Yes, welcome everybody to our first official fabulous webinar on micro-optics for automotive. So I think we have a really interesting lineup of speakers. So we will start with Eugene from CSEM, then Albert from G Square Industrial Engineering, Raúl from Microrelleus, Daniela from FORVIA HELLA, Jonas from Wielandts UPMT, and we will finish with Sébastien from Alfamation. So with that, I would actually like to give the floor to our first speaker. The floor is yours.
Great. So thanks for having me here. My name is Evgenii Glushkov. I work for CSEM, and I will talk about micro and nano optics for automotive applications. But before that, for those of you who don't know CSEM, I will briefly present it. We are a Swiss technology innovation center, not for profit as well. And our mission is to develop and transfer new technologies to the industry. And we've been doing that for many, many years. And we've worked with hundreds of industrial partners in Switzerland and all over the world. So a quick overview of the variety of projects that our clients ask us to work on. You can see here applications in the watch industry, in rail inspection, and atomic clocks, and also in bioengineering. So from that, you can probably understand that CSEM has a lot of different directions. We are very industry focused. We have a lot of staff with industry experience. We offer long-term support, and also we have our own clean rooms and our own processes and certification. So this is our specialization. Of course, there are many directions which I will not mention today. They will be focused on micro and nano optics, and this is what we can offer at CSEM. So from a component level, where we develop different components from nano optical systems to micro lenses to peak photonic integrated circuits and imaging sensors. Then we can provide different design capabilities and processing capabilities, and assembling the full systems, be it cameras or LiDARs or sensing systems and modules. So this is CSEM at a glance. And now diving deeper into micro and nano optics, what we offer are, of course, simulations and designs of optical components, then microlens arrays, microstructures for beam shaping, and also for detection. So for arrays of detectors, we fabricate microlenses. I will show an example of that later. And of course, different nanostructures for various applications, for security features, and so on. So these are our technology bricks. And how we do it, we have our own clean room in Neuchâtel. For those of you who've been to Switzerland, it's situated in on a biggest lake that is completely in Switzerland, maybe a bit less known from outside. And we have a very nice clean room. We can work with up to 8-inch wafers, and having also few important certifications and a specialized microlens foundry service. Then for those of you who want to know more about how we work with micro and nano optics, this is our standard process flow. So we start with design and simulation, then we do we produce some master structures, we produce some molds and prototypes on up to 8-inch wafers. Then we can scale them up using different technologies for pilot production or volume production. And of course, on every step, we use metrology tools to quickly reiterate and ensure that fabricated structures are within the specs. And then we can go back to simulations and simulate how the real fabricated device performs and what to expect from it. So in terms of simulations, we are doing everything from ray tracing to wave optics and nano-optics, adapting the tools that we use to the scale and to the problem that we're trying to address. And here again, being very, very flexible depending on customer needs. So this was a brief overview, and now more into applications. So I will describe a few projects that we had with our customers. And one of the standard projects is, of course, putting microlens arrays on active imagers. And here you can see an example of such an active imager. It's a single photon avalanche diode array. And we are putting microlenses on top in order to increase the detection efficiency. So photon detection efficiency, collect more photons, guide more photons to the active area of each pixel, and not to the space in between them where they would be lost. So this increases the overall signal to noise ratio, and this is a standard offer that we're providing to our customers. And you can buy such products on the market. A second example of applications which might be also useful for automotive is surface nanostructuring. Here you can see that we're able to make optically visually attractive nanostructures on different materials, from metals to foils, ceramics, and polymers, and they can produce different visual effects, which can be used either for styling or for counterfeiting applications. So so-called optical security features on banknotes and so on. Now for automotive, as I'm the first speaker, I can briefly present where optics and micro-optics could be used. And it's no surprise that there are many modules and modern cars that are using optics. And I will not talk about all of them because there will be many speakers after me, but I will focus on signal and decorative lighting, which is also one of the projects that we worked on at CSEM with various industrial partners. So again, brief reminder why we want to work with micro-optics for automotive is because it's miniaturizing the components, so you get you save space, you save weight, you can be more free in your styling options because your optical elements can become invisible or more integrated, so improve aesthetics. It also provides new functionality, and it's more efficient, so you can save energy and improve the light distribution. So the last 2 points are illustrated also by this application of using micro-optics for signal and decorative lighting. You might heard or you might seen already some light carpets which are fueled by micro-optical components, and these produce novel optical effects in modern cars already, but the whole spectrum of functionalities that are enabled by such light carpets is actually much wider. So you can think of reverse warnings or turn signals projected on the ground. And this is exactly what microlens arrays can be used for in automotive lighting. So you can imagine producing microlens arrays of hundreds or thousands of microlenses of different diameters, different shapes. This is something that we are doing at CSEM with the full cycle development from design and simulations to fabrication metrology and then upscaling of such microlens-based devices. A little bit deeper dive into our workflow. So we start, of course, with design and simulation of such projection systems. So we have standard industry tools for these purposes, as well as some internally developed tools, and we can simulate and estimate how the projection would look like on the ground, depending on the optics that you use, depending on the light source that you use, and as well your pattern. And we can, of course, optimize in simulations different performance metrics, be it brightness, resolution, or homogeneity of the projection. So here, for example, is our quantitative evaluation pipeline, how we are assessing the characteristics of the projection, so we can perform some analysis of a grid of lines, for example, to see what are the characteristics of the projection and how we can improve them. And of course, few main characteristics I already mentioned. These are brightness, resolution, homogeneity, and of course you cannot optimize for all of them at the same time, so you need to find a certain compromise depending on the application. Here, for example, you can see how the choice of microlens array, collimator, and your light source influences the projection. And of course, you need to pick the right combination before going to even small scale production. As a next step, we can think of actually performing a multi-physics simulation to further adapt our design to the real material that we're going to use to fabricate these structures. So here we developed also an internal tool which compensates for the shrinkage, which is a well-known effect in imprinted optical micro and nanostructures. So here we can apply a certain shrinkage compensation afterwards so that our final structures are according to the specs. And here, of course, we can adjust for various environmental factors and material options that we have. And as a final step, when you want to upscale your imprinted micro or nanostructures, we're often using a step and repeat machine, which is rather unique and can allow you to replicate your microlens arrays. An example is shown on the right. And you can replicate hundreds of such arrays on rather big substrates, so bigger than even the 8-inch wafers that are available in the clean room. And the advantage also that it can be used to replicate freeform micro and nano-optics, which is quite challenging to do on standard wafers and with standard processes. So this is also one of our offers that we can offer to the clients. And with that, I will finish my presentation. So if you have any questions, you want to discuss anything I mentioned, feel free to write in the chat. There will be a Q&A, and also feel free to shoot me an email afterwards. Thank you.
Thank you so much for being here and for your presentation. So very good.
Thanks, Jessica. It was a pleasure.
Very welcome. So our next speaker is Albert, whom I'm very happy to introduce. That was also a part of our FABULous project. So I would be happy to hear you a little bit more about what we've done and your other capabilities for this market segment. Go ahead, Albert. Thank you so much for being here.
Yeah, thank you, Jessica, for organizing this great event and also for hosting us here. So, as you mentioned in my speech, I will talk a little bit about our feasibility project we did within the FABULous consortium, also working in a close collaboration with Joanneum Research, and the quite positive results on the project and our next steps. What we are talking about, so basically we are talking about reflectors for the automotive market. So I'm sure you have heard about them, or at least you have seen about them, most likely on your bicycle. Yeah, that's typically on your wheels, but in the automotive market, you all are experts. We have the reflex reflectors for the North American market on the front headlamp. You can see one example here. And also for specific applications like trailers or trucks. There are red applications in the rear lamps. The current situation, just to give you a little introduction, what we are talking about. I know from experience, just one example for headlamps, you need approximately 25 square centimeters to achieve the legal requirements. Yeah. Typical optics nowadays have 2 to 3 millimeters in size, and this depends purely on the tooling concept. And this is also the first problem we are facing with this tooling consists of single pins. And therefore, these pins make the tool quite complicated and expensive. And also, that's the second point, there are more or less one or two tool suppliers which are able to do this tool technology in Europe. So this makes it even more complicated and complex also in the supply chain. So far as we did some market research also, we did not observe available micro-optics for this kind of reflex optics in the market available. So just in one sentence about the optical principle, it's basically quite simple, one of the most simple laws in physics. So this pyramid structures consists of three surfaces which are arranged in a way that the light ray is totally refracted in the direction where it comes from. So it's a passive element and not a lit up element. So what did we do in our feasibility study together with FABULous and Joanneum Research? The first step was to develop an algorithm for the calculation of the surfaces. So it was not that easy, as you can imagine, to make some surfaces in Lucidshape or CMAX or wherever. So we really needed to develop a specific algorithm for the calculation of this small optics for this specific function. What you can see here are screenshots from the simulations we did. It was basically quite complicated. It does not look so, but it was. So we used here 10,000 of rays per angle, which leads to the simulation result on the right side. And to explain this one, so the simulation setup was quite simple. There were incoming rays in a specific angle, and we observed in the simulation how the total refraction is performing with the pyramid structures. Just to spoiler a little bit, we are talking about 30 microns of height here for the pyramid. Here on the right side, you can see the result of the simulation. Just to explain it a little bit, here on the right side is the refraction and dependent on the angle of incidence of the light ray. The dotted lines here represent 10 degrees. So what you can see clearly in the middle, up to about 20 degrees, the reflectance is really close to 100% of the emitted light you get back. And this corresponds quite good to the legal regulations regarding SAE and also for ECE for the Wielandts in case of a red retroreflector. Regulation was quite good, and for this purpose, up to 20-degree angle, the reflectance was more or less perfect for the ideal surface. The next step was then the origination. Yeah, the target, as mentioned before, was to produce pyramid microstructures with this special refractive behavior. And the way it was done by uranium research. They have the appropriate machinery and microscopes to do the quality control. Was the origination of the structures, and that was carried out by using the maskless grayscale laser lithography. You can see it here on the left top picture. This was the structure design. And for the laser lithography program, so to say, the inverted structure to bring it to the material. The grayscale laser lithography, of course, uses a photosensitive resin, and the areas of the, let's say, the top of the pyramids and the bottom are exposed to a specific light dose on the substrate to get out the needed 30 micron height structures. The quality control, of course, every step was controlled by scanning electron microscopes, and you can see here on the left bottom picture the image of the SEM analysis of this origination. And you can see quite sharp edges, so it is, so what you can see from the pictures, more or less also perfect. Of course, we also characterized, or uranium in that case, characterized the radii here on the edges and also the angles of the surfaces, which is the most important parameter here. But I did not add all these details here. We can see it in the summary what happened with the detailed measurements. Yeah, next step to come to a functional prototype was then to produce a durable master, and this was done by coating this laser lithography structure with a nickel coating. This results in a stable master we could use for the replication. That is the most important part, to get some physical parts and prototypes to do some light lab measurements as well. What you can see here on the left top picture is the metallized master. Just for your information, this is 1 square centimeter, so we are talking about 10 millimeters by 10 millimeters with the pyramid height of 30 micron meters, just for remembering that. Also for this process step, after the nickel coating, there was done an electron microscope scan to check the quality of the surfaces, and what we could observe already here, that the radius increased during this nickel coating. But that was something we expected, so nothing dramatically in theory. Last step, of course, was the replication to get really some physical parts, and this was done by UV imprint technology. And what you can see here on the right side already is the microscope check of the physical parts of the prototypes. With you see it here, the scale is around about 30 micrometers. So you can see that the size of the pyramids is really around about 30 microns. What we observed together with Joanneum, or what Joanneum observed in that case, that the inclination angles, you remember that the angles of these pyramids are the most critical factor to get the total refraction. These angles changed a little bit during the production process. So that means that the slope of the flanks are steeper. Yeah, there were different lengths and heights compared to the simulation. And of course, you will see it in the measurement results that will lead to a slight deviation. But at least we know the reason for that. And I will explain it a little bit later what the defect was. So this is probably the most interesting slide for the optical engineers in the participant list, the measurements. Yeah, for an ideal comparison, we took an ideal mirror here. You can see the results here on the right top picture, where you can see close to 100% reflectance in the center zone in 0 degree vertical and 0 degree horizontal. The second one was a typical white tape, which is available on the market, used for different applications like trailers or agricultural machines, wherever there are no strict laws, but you need some reflectance to see the machines. Here, the quality was surprisingly good. You can see it in the second top picture from above. The reflectance was about 80 to close to 90% over a quite acceptable angle for this application. You have to imagine these tapes you can buy meter by meter, so it's no small device, and this quality over a high volume production is quite good. The third sample, this one, you can see it in orange here, was a typical reflex reflector we bought also in the car supply market, and cut it in a rectangle shape to have a reference about a real automotive and homologated part. And surprisingly, maybe there was some defect in the measurement, but surprisingly, this standard component from the market did not perform as we expect. So it was quite diffuse. There was no central spot recognizable. So in my personal eyes, this would not be sufficient for doing a homologation for European or American market. The last one is now the sample produced. Yeah, it was put in this black mask to have a better, to be able to hold it, as the structure is only 10 millimeters by 10 millimeters. And what you can observe here, also here we had a small surprise. You can see a quite good reflection in the center. So basically the system works, but the negative aspect, and this is caused by the different angles in the prototype, the reflectance is only about 10 to 15% roundabout. So this is definitely not the target. So this was a small deviation, but nothing bad, because a feasibility study also can have negative results. Yeah, a conclusion to these steps. We did the optical simulation and confirmed the functionality, basically for these 30 micron structures for this function. The microstructures were successfully fabricated, but the expected measurement results were not realized. The good thing, we clearly know the reason for the insufficient results, namely the maskless grayscale laser lithography calibration was not perfect. That means the machine used for this lithography was not perfect calibrated, and due to the time and cost frame within this project, we had no chance to do a second loop. But yeah, it's well known where the problem was and how to compensate it. Here we can see a direct comparison. Yeah, this was this retroreflectors you can buy in the market. I'm sure you have seen these red triangles on the motorway on some trailers. The basic approach of this project, or one main approach, was to give automotive designers more freedom to generate better headlamps and rear lamps. This is just some pictures I took from the internet in the morning, so to get the history. So this was a typical automotive thick wall optic with optics like 2 millimeters, 5 years ago, 10 years ago. And the approach of many automotive designers is a smaller optics. I know from experience some OEMs in the meantime require 0.5 millimeter optics. And what's also going on, I found this beautiful press release here from FORVIA HELLA with their new flat light technology. And you can see clearly what was the target, that you have a pure homogeneous surface without any visible optics also in the cold impression. So this was a main approach, and it's hard to see on the picture, but you can imagine it. I guess you all are experts. From this old 3 millimeter optics to a flowless design where you cannot see any optics anymore with your eyes. Yeah, I just want to mention it on the side. By the way, special thanks to Joanneum here, Institute Materials, and to PHABULOuS. Within this consortium, it was possible to realize this feasibility study. And it was so innovative that our company won an innovation award. It was like 2 or 3 weeks ago for innovative services in the automotive market with our project. So we are really proud of it, and we are even more proud of our partnerships. Maybe you ask, or one question always is, okay, you have now this 1 square centimeter prototype, but what's going on now? So the next steps are, and there is one lead customer in Austria with whom we are performing these next steps. As mentioned, there was some mistake during the laser lithography calibration, so we recalculate this algorithm to correct the angles we observed in the prototype. Second step then is we already had some discussions, but they will go into deeper discussions the next month to get suppliers, because it's not so easy as you can imagine. We already heard one speech before to get this micro-optics in the tool. One of our approaches was not to have some foils or something like that, which would be more easy by having a round master and the endless foil, but that's not so easy for automotive applications. So our work is now to find a good tooling partner who has experience in diamond turning and ruling to really achieve this 30 micron optics in the steel tools for injection molding. And of course, injection molding, it's also not super simple, and it cannot be done on every machine, and not every supplier can do it. To use these special tools then for the injection molding of the plastic part. The next planned step is a kind of a prototyping tool with a small surface of about 50 by 50 millimeters. And the target is here to really go on the injection molding machine to try out if the optics are coming out, if the quality of the tool inserts is good, if all the coatings are good, how many pieces we can produce without quality loss, and of course one loop in the light lab to characterize the lighting behavior. And the last step, but it's some month ahead, will be the full-scale production, where it is planned to generate such a trailer triangle like I've shown in the picture before with the micro-optics. They of course have also legal requirements, and they have more than 100 square centimeter, which is quite a lot for 30 micron optics. So here we want to learn and learn from the pre-series how this master machining works in the tool, how this tool can be manufactured without quality loss, how the molding of the part works really for thousands of pieces, and if there are some negative aspects in the validation we did not consider so far, maybe. So there are some steps ahead, but I'm glad that we have a partner or customer with whom we can do this next steps. Yeah, I'm already coming to my end. So whenever you have some questions, please use the Q&A field, and I would like to thank you for your attention.
Thank you so much, Albert, for your presentation. And then we will go now to the next speaker. So next speaker will be Raúl García, CEO of Microrelleus. Thank you so much for being here. And
Jessica, thank you.
Yes, perfect. So you're here. Yeah, I would say the floor is yours. Go ahead.
Thank you so much for the introduction. I am Raúl García, General Manager of Microrelleus, and I will speak today about what we are doing to enhance automotive lighting design and functionality through direct tool microstructuring. I will speak just 1 minute about who we are and the manufacturing process. We engrave injection molds, and then we're going to focus directly on the production tool engraving, lighting prototypes, a case study that summarizes the previous points with the Cupra, Formentor, and Leon, And then at the end, I will speak about a new service comparing prototype and production part, where we got some support also from PHABULOuS for the initial stages of the study. So regarding who we are a services provider for industry. What we do is laser microstructuring, surface texturing, and industrial engraving since 1983 from Barcelona. In 2016, we were world pioneers offering femtosecond laser services in 5-axis. In 2022, pioneers with big machine for big and heavy parts. Regarding the manufacturing process, from the original micro-optics design concept idea of the part, there's the manufacturing of the mold. The mold maker is doing the mold inserts, the mold, which is going to be injected, the part developed. We are going to engrave that standard mold, engraving thousands of microprisms, micro-optics, or engraving textures for light diffusion. And at the end, we are going to have the final injected plastic parts going in production. And we are engraving molds using an ultra-precise laser, which is called femtosecond laser, that has some characteristics that we can see here. Clean engraving with sharp edges, absolutely burr-free, high-quality surface finishing, excellent tolerances, and we can engrave over any material. It has a very, very small radius, down to 7 microns, so we can engrave smaller details than ever before using conventional technologies in absolutely standard molds and tools for new possibilities in lighting. And how do we use this technology in lighting? What we do is engraving molds, but we engrave microstructures and microtextures. We engrave freeform microstructures and micro-optics with smaller details and better tolerances for new design and functional possibilities, and textures for controlled light diffusion, both in the mold or in the prototype parts imitating VDI textures, for example. We'll see some examples later. Regarding production tool engraving, when we engrave directly the injection molds, this is we're going to see a couple of case studies. This is one. This is some engraving done for our customer Odelo. We engraved thousands of freeform microprisms. Here we can see the images of the microscope images of the mold and the effect on the right-hand side. So depending on how you look to the part, if it's illuminated, you will see those logos there, or you will see a complete homogeneous surface, because the prisms are sending the light in the correct direction, in one direction or in another. Another example is Illuvision product of our customer OP Mobility. We engrave thousands of micro-optics in the mold, as we can see on the top, to have the nice product that we can see on the bottom, which is the Illuvision project. Yes. It has ultra homogeneous appearance, super thin frameless design in a simple concept, fully 3-dimensional shapes with semi-transparent appearance. So where, in which cars in the market we can see products engraved using the femtosecond laser, the ultra-precise laser. Some examples are the Renault Rafale for the micro-optics on the lines, the DS number 8 for the micro-optics that illuminate the logo, Range Rover Sport, thousands of micro-optics behind the tail lamp to have this nice homogeneous appearance. Cupra Formentor and Leon, we'll see the example later. Lancia Ypsilon by engraving homogeneous diffusive texture over the pillows to avoid the hot spots of the LED, or Fiat Topolino. We can achieve some other effects also by engraving the mold and injecting any plastic. In this case, for example, anti-glare. So we have ultra low reflection on the plastic injected part that can be PC, PMMA, ABS, etc., just by texturing the tool. applications, bezels, housings, etc. Any part where you want to avoid reflection. Here we can see image of comparison of the reflection with of our anti-glare texture compared with standard BDI textures in the market. As you can see, the difference is really, really huge. So continuing with the production tool engraving, but in this case, texturing, we have this microscat technology, which is micro-texturing, microstructuring for light scattering control from tool. We are engraving the mold, and by injecting transparent material, you can control the diffusion of the light. The two parts on the left are transparent material injected, but as you can see, they have this milky, nice finishing, and we are avoiding the hot spots of the LEDs behind just by the engraving on the tool. We have different references depending on how you want to open the light. And if we compare this microscat engraved in the mold and injecting transparent PC or PMMA with standard textures or standard materials in the market, what we can see is that if we compare with similar depth with BDI, we see that our microscat reference 30 has similar depth than BDI 24. But as you can see, we are avoiding completely the hot spots of the LED, while with the BDI 24, you can clearly see them. Or if we compare with DF material, in this case, DF 23 2mm, we see that we open more the light with our MSC 40 than with this diffusive material. Some applications in the market, or some applications of the texture, 3D shade diffusive areas, over microstructures. For example, if we engrave some microprisms for a surface light guide, a light curtain, if we engrave in an addition of the microprism, the microscat over the prism, we are going to avoid the hot spots, the torches of the light, getting a better homogeneity without losing too much light. Or on reflectors, if you want to increase the diffusion of the metallized surfaces. How it works? Very easy, just simulation and decision. Use the files for Speos Light Tools Lucid Shape and decide which is the reference, the correct reference for the purpose. We are going to engrave the mold, and the mold is ready for plastic injection. Very, very simple. Benefits: environmental, material reduction, easy to recycle in terms of design, high quality surface finishing, invisible pattern, possibility of ultra thick pieces, and design just on the areas that you want on any kind of 3D curved tools. Cost effective, energy reduction, reduction of material injected and weight, no need of expensive diffusers or films, and process simplification, as explained, just tool engraving and injection. We can engrave also prototypes. Here you can see same part injected or directly engraved, or VDI imitation, imitating grain size, grain depth, grain distribution, much, much closer effect than using, of course, sandblast or paint in the prototype. Or engraving thousands of microprisms, micro-optics, like the Cupra Tabascan concept here. This case study, it's a real project in the market, Cupra Formentor and León, is a nice example because we have participated in all the stages, and it covers a little bit everything. So there's the original customer request, this new concept of the tail lens, the LEDs coming from the top. There will be thousands of microprisms all around the blade, and that will send the light 90-degree or in the correct direction. There's the microprisms concept for this light distribution. There's the engraving of the PMMA prototypes, the engraving of the production tool inserts, and the engraving of the microscat over the prisms and on the sides of the blades. Why? To have this nice 3D effect, but also to avoid strange reflections of the light. This is the final effect that we can see in the street with the Cupra Formentor and Cupra Leon just by engraving an absolutely standard mold, standard tool. Regarding the capabilities, we just don't just engrave the molds. We can support in development, optical design, optical simulation. We have our own optical team, consultancy, measurement, mock-up, production. So we offer a unique value proposal by combining laser engineering, optical engineering, and manufacturing. This is the project I told at the beginning, which is our light match service. So if we analyze how the part is done in all the process, from the original optical simulation of the part with the micro-optics, there's the PMMA prototype manufacturing, then there's the photometry analysis of the PMMA prototype, there's a comparison with the original simulation. Months after, even years after, there's the tool manufacturing and the injection of production parts. Then there's the photometry analysis of the production parts in comparison with prototype and with simulation. And then you realize that there is always misalignment. Our proposal is in the very beginning of the steps, in the PMMA prototype step, when we engrave the prototype, we select some specific area of the prototype, and we are going to manufacture exactly that part. And we are going to manufacture two of them. One will be manufactured same process than the prototype, PMMA milled part and directly engraved with the femtosecond laser. And we are going to manufacture an insert for our test tool by engraving the same optics on the insert. And we are going to inject. So we are going to have two parts of some specific area of the prototype. One has the same method of engraving and manufacturing than the prototype, and the other has the same method like the production part that will be months later in the future. We analyze the photometry of both parts, injected and prototype, and we see some deviation. So imagine 10%, 15, whatever. This is very valuable information because customer can extrapolate the information on the prototype. So they can have a lot of information from the very beginning, and they know what they can expect months before, after on the production. This is a little bit of information regarding what I just explained. The simulation that we do, everything done in-house in Microrelleus, simulation, prototype engraving, tool engraving, tolerance analysis, and the photometry. Here we can see a specific example for a light curtain, and that's the kind of analysis we send to the customer in terms of photometry. Regarding patterns, we can develop any texture, pattern design from the surface design or confocal microscope analysis, algorithm texture development to have it infinite, to be able to engrave any mold or any part, texture engraving, mold injection, analysis of tolerances, photometry, whatever is needed, and implementation in the mold. We support the complete optical surface value chain from the beginning with the OEMs, specs definition, concept R&D, optical consultancy, proof of concept, etc. Tier 1 on the design, development, validation, prototyping, feasibility, etc. Mold makers by manufacturing the tool if customer wants, or just by engraving them. And in tier 1 again on the production of the parts. As a summary, ultra-precise laser microstructuring and surface texturing, nano and femtosecond laser engraving on production tools and prototypes, optical insert manufacturing, Microrelleus lighting laboratory, all that we have seen, the optical engineering in-house, simulation, prototype, injection, photometry, our light match service, and who our customers are. All the companies, mainly OEMs and tier 1s, also tier 2, mold makers, plastic injectors, etc. So thank you very much for your attention. If you have any doubt, I will be happy to try to answer it. Thank you so much.
Thank you so much, Raúl, for being here and presenting your capabilities. So next one is Daniela Karthaus from FORVIA HELLA. Thank you so much, Daniela, for being here. You will talk, of course, a little bit more about, the different ways to use micro-optics in automotive. So I'm very happy that you are here, and the floor is all yours.
Thank you. I'm so very happy to be here today. So today we have already heard a lot about micro-optics for automotive applications, and I'd like to discuss with you whether we see a breakthrough of these technologies soon, or do we take the last hurdles or not. Before we start that discussion, I'd like to shortly introduce FORVIA HELLA. So we have a really long history. We were founded in 1899 in Germany, and today we are in more than 125 locations with more than 36,000 employees worldwide. Not so much than 300. But the most important aspect, of course, and most interesting aspect here is our product portfolio. So in 2022, we joined the FORVIA group together with the company Faurecia. And as you see here, let's use the laser pointer. As you see here, Faurecia is focusing more on the interior equipment, on clean mobility, and also part-wise electronics. And on the other side, HELLA is focusing on electronics, lighting, and lifecycle solutions. And today we look at our developments in the lighting business group, and there we see that we look for headlamp systems, rear lamps, interior lighting, and also car body lighting. Yeah, and in this business groups, we have also a long history of developing micro-optics. You see here a timeline starting in 2013, and it does not end today, but of course, the results are until today. And you see here not specific products, but you see an overview about the different micro-optic sizes we are looking for and the different applications in general. You see that we already started in 2014 to use really small structures in the nanometer range for 3D effects. We look also for much larger structures for projection with 400 micrometers. And there are a lot of in between. You see that we have a lot of diffuser optics developed. We have here optical stacks. And it goes also about freeform micro-optics and now also nano-optics for stoplights. So there's a huge range. And I'd like to highlight some of our achievements in detail. So what have we achieved? First, the integration of large-scale micro-optics for different applications. But one example is a typical example that you all know, an MLA for a headlamp module. You see it here in the picture, and here we are talking about structure sizes in the range of 400 or 200 micrometers. Then we also successfully integrated micro-optics in optical stacks. We have already seen a picture of our flatline module where we use different optical layers that we combine together in one module to realize a really homogeneous appearance with a high efficiency. And we use this, as you see here, for rear lamps, but now we are also developing this for daytime running light. And one further achievement is the integration of, for example, holographic elements, as you can see it in the image below, where we want to generate decorative holograms for 3D effects, but also functional holograms is a great topic for us. And of course, diffractive optics or diffractive-refractive hybrid optics, especially when we look for diffusers. Another achievement is not the integration, but in general, the POCs that we already performed, for example, for micro-reflective optics, for freeform micro-optics, and also meter optics. You see here an example of a meter optics-based projector, where we project the logo of our lighting research department, ELAB. And I like to also show in detail our achievements concerning the freeform micro-optics together with the PHABULOuS pilot line. So in the PHABULOuS project, we evaluated different mid-scale microstructures. This means we had a range of structure sizes from 80 nanometers to 250 nanometers roundabout. And we want to realize high and low beam functions with these optics. You see here the different structure types, for example, more like a Fresnel lens, facet structures, something completely freeform, I don't know how to describe it, and also combined double-sided elements. And yeah, the first results were really poor, as you see it here. These were the first tests where we had a really small angular range in the horizontal direction. We had a really bad efficiency of about 7%. And I think only the people here in the call who are familiar with evaluating headlamp systems can see the tendency of low beam distribution here. So we had a huge amount of stray light. About 1.5 years later, we realized this light distribution here on the right side. So there we had now a great angular range achieved in vertical direction, also a bit too much. So there we can reduce it again. We have an acceptable performance of 30%, and well, the contrast is compared to the first trials acceptable, but far away from what we need to achieve. So here we have more effort to realize this, and this is still on our agenda. We realized a demonstrator setup, and maybe you have seen it already because Jessica is carrying it around. And you see here a kind of vertical slim module. One element, as you can see here, is 10 by 10 millimeters, and it's really thin from LED to the element. And yeah, it shows really in a great way the potentials of freeform micro-optics for headlamp applications and of course in general. And yeah, when you see that, you might ask yourself, so why don't we have already a widespread use of micro-optics? So it sounds all really nice, and we had so many developments, but I think some challenges you have already heard in the previous presentations, and I like to underline them. So what we haven't achieved yet. One point here is that we want to use small and mid-scale micro-optics for headlamp distributions. Small and mid-scale means small more in region of going to diffractive elements, and mid-scale in the region of 60 to 80 micrometers. And to use these optics in a white light, small package system with a high contrast is really, really a high challenge. And the reason, on the one hand, is that we need to find a mastering solution for these mid-scale optics. You see it here in the image. You see here a design in gray and a sample structure in yellow. And you see on the one hand that we get roundings at the edges, and on the other hand, the modulation depth of the structure is reduced when we or when the periodicity of the structure is getting smaller, or say it in other words, when the slope angle is increasing. And especially when we look for our structures that we evaluated, we have not found a mastering solution for that yet. Then the combination of small-scale micro-optics with white light. This is a really clear and well-known issue, that we want to use diffractive or hybrid diffractive refractive optics with white light LEDs, and especially when we want to go for a headlamp application, this is still a challenge to find a good solution and to avoid color effects and dispersion effects. And the final point is the imprinting material, especially when we look for nano imprinting or UV imprinting in general. We see that there's no, or we have not found a material yet that resists our automotive conditions. So when we bring, let's say a glass element with an UV resist on it into our material tests, for example, a thermal shock test from -40 degrees to 120 degrees, then we see delamination delamination effects or cracking or something like that. And therefore, we still look for a solution for that. And finally, things we haven't yet looked at. So sustainability. I made a small research on that, but the publications are really a few number of it. So especially when we now look for the CO2 footprint, for example, of manufacturing, or especially for mastering of micro-optics, when we want to use them, for example, for UV imprinted optics or sustainable materials. As I mentioned, when we now find a solution for having materials that resist our conditions, so are they sustainable? Can we recycle these type of optics? These are all questions that we will be faced in the future, and especially FORVIA HELLA is really looking for solutions for the future products for that. And yeah, I would be really interested if somebody here has already a solution and like to discuss with us about that. And with this, I'm already at the end of my presentation. And yeah, you're welcome to ask questions, to give me any comments on that, or just to connect. Thanks.
Perfect. Thank you so much, Daniela. Then for now, we will continue on with the next speaker. So next speaker in line is Jonas from Wielandts UPMT. Jonas, thank you so much for joining us. The floor is yours.
Thank you. Okay, thank you for attending this meeting. So today I'm going to talk about our solution for maskless freeform lens arrays for projection lighting. So to answer Daniela's question, do we take the last hurdle? Let's say maybe this is part of an answer, but let's move forward. If this is working, yes. Okay, maybe in a few words, who we are and what we are doing. So the business is based in Belgium. We are still a small team, at least much smaller than HELLA, of about 15 people. And we are offering ultra precision manufacturing services for manufacturing of complex optical and mechanical components. We have developed different technologies to do that, and I will briefly go and dive into those different technologies we have, such that you understand a little bit the context before we go to maskless projection lens arrays. As some of you may know, one of our main technology, we have called it DPI, is a machining technology that allows us to diamond turn lens arrays with the highest quality. I will briefly go to that in one moment. So today we are using this technology to manufacture molds or inserts and sell them to customers. Then besides that, we had some customers saying, okay, you can make very nice and special molds. You are very inventive to make tooling, but we also struggle to find some people replicating optical parts. Can you also offer replication services? And that's how we started having in-house replication processes like injection molding and other. One last point, maybe less of interest here, is that, of course, we have developed a lot of know-how related to diamond machining, ultra precision manufacturing in general, and we still offer that as a service eventually for making like infrared lenses, space mirrors, and things like that. But obviously, we try to focus our activities on the applications where we have some specific technologies. And just for you to understand what DPI is. So DPI is based on diamond turning. And today, diamond turning is the reference process for manufacturing of optics replication tooling. Of course, not as small as what we have seen earlier in the earlier presentation, but let's say larger optics like smartphone optics and things like that are nowadays injection molded parts that are all relying on a diamond turned insert. So diamond turning really delivers highly accurate shape accuracies and very low roughnesses that achieve very good quality for optical replication toolings. So our idea, the problem with diamond turning, and this is a picture of a diamond turning machine, problem with diamond turning is that it is a turning process. So normally you are only able to turn a rotational symmetric part with its axis aligned with the axis of the machine. So if you are turning a single lens, like a smartphone lens, it's quite easy. You will take the insert, align the optical axis of the optical surface with the axis of the turning machine, and you will turn it. However, when you want to make an array of optical surfaces, it becomes much more tricky. So our idea was to develop a solution to solve this. And this solution is now a patented process, which we have called DPI. Basically, how does it work? We are sequentially aligning the optical axis of each optical surface you want to machine on your substrate, such that you are machining it as if it's one single lens. So we don't add up any limitation to diamond turning, and we can achieve the very good quality of diamond turning on each lens of your array. It can be two-axis turning, it can be freeform turning, so you can make an array of freeform lenses, for example. Maybe just for your information, a few use cases we've worked on using this technology. Obviously, we've made sensor applications, augmented reality applications with other, not with DPI, but with other processes. We've also made like decorative topics, healthcare applications, and obviously automotive applications. So we have machined multiple masters for headlights, for ground projection, and stuff like that. Okay. Now, a few words about our replication processes. How it works, it's very easy. Obviously, we have diamond machining capabilities in-house. So we will make a replication tooling like this metallic part, which is an array of freeform lenses. And we take this tooling, metallic tooling, and have two different processes in-house. One is injection molding. The other one is a very specific compression molding solution, which I won't talk about today. Let's say this one allows us to achieve much, much more accurate and crazy geometries compared to injection molding. But let's keep injection molding in-house because it's highly, the productivity is so high that it remains a very good process if the geometries are applicable to that. Okay, now let's go to projection lens arrays. Definitely the topic, I think we've heard enough about it today, so I don't need to explain you what this is. So you can have ground projection, headlight projection systems. Actually, the technology behind it today is the same. How does it work? I think we had someone from CSEM explaining it very well. So the current systems work like that. You have a glass wafer. On one side, you will imprint a chrome mask. And on both sides, you will imprint a lens array, such that when you shine light through the mask, and then project the image created by the mask on the screen. It can be a street or it can be at infinity for a headlight system. But that's basically how the system works. There are a few limitations with those systems. One is the throughput is potentially quite bad because you are blocking a lot of light with this chrome mask. So eventually the throughput can become very, very low. Another one, and probably the main one, is the cost of those systems. It's a quite complicated process with multiple different processes involved. And at the end, the final cost of one module remains a hot topic for current OEMs. Last one, which is also related to the throughput at the end, is that you can basically not make or not easily make grayscale patterns. So if you want to make grayscale pattern with this, you basically need to block more light in certain of those channels such that you decrease the intensity of the lighting in certain regions of the projected pattern. But this actually comes with additional cost in terms of throughput. So knowing that, we thought, don't we have in our hands some solutions to come and to solve these limitations? And basically, for a very long time, I had on my desk this lens, which is a refractive freeform lens. Nothing new there. It's a very well-known technology existing for a very long time. So basically, it's a continuous surface that is designed such that it redirects rays of incoming light onto a specific pattern at a certain distance. What's very nice with that is that this lens can be direct diamond machined by diamond turning, or it can be replicated by injection molding using a diamond machined molding tool. Well, this is something we liked, obviously, because we have diamond machines in-house. So we can make these lenses or these tools. Plus, we have a very nice technology, which is called DPI, which allows us, in theory, to machine not only one surface like this, but arrays of surfaces like these into one monolithic molding tool. So our idea was to make it an array of freeform surfaces such that, in theory, we can have high throughput, lower cost because of the manufacturing steps involved, which are making a mold and then injection molding, while keeping the advantages of micro-optics arrays, like sizes, as it has been mentioned before. So what does our system look like? So basically, we are using a light source, collimation lens, just as the existing systems, and an array of optical channels. The only thing is that we are replacing the chrome mask by the double freeform surfaces. So we have, instead of one single element, we have two elements. One is containing a condensing lens on one side and a freeform surface on the other one. The other element is another freeform surface and a projection lens. Then you define a target plane with where you want to project a target image. Very quickly, why do we have all those different surfaces? Well, this is probably an obvious question. Why do we add a projection lens? Well, this is basically coming from the fact that we currently have no zero étendue or perfect collimation lenses. So, of course, if you have a zero étendue or a perfect collimator, then you have a wavefront with a perfectly planar wavefront incoming your freeform surface, and then you can easily redirect this ray onto at a predefined location on your target plane such that you obtain a perfectly sharp image. Unfortunately, these light sources don't exist, and you have extended light sources such that instead of having one wavefront, you have multiple wavefronts incoming your system, which means that at each position of your freeform optic, you have multiple rays coming in with different incoming angles, such that when you project that onto the screen, you have a blur, which is directly linked to the distance of this target plane and the extension of your light source. So the furthest away the target plane, the more blur. So to avoid this, you add a projection lens. Instead of creating the image on the final target plane, you calculate your freeform surface to create this image on an intermediate plane, such that you minimize this blur. And then the projection lens captures this image here and projects it on the target plane, and the blur remains proportional to the size of the target of the projected image. So this is already a good point to minimize the blur of the projected image. Now, why do we have an additional second freeform and the condensing lens? Well, this is mainly to avoid crosstalk or losing some rays. Very quickly, why do we have that? Well, imagine you want to have this ray redirected at this place on the intermediate image plane. Well, eventually, if you continue this ray, it is not captured by your projection lens. If it's not captured, then you are starting to lose a lot of rays, and eventually it's captured by the neighboring channel, which screws up your entire projection. So to avoid that, we add two surfaces. One is a condensing lens. The second one is a second freeform. And with these two elements, you can basically redirect this ray to make sure it is captured by the projection lens, such that at the end you have a very nice projection quality. Okay, this is all theory. So we have developed our calculation algorithms to generate those two freeform surfaces. This is one simulation result. But we, of course, did not just want to think about a concept. We wanted to apply this concept to the limitations of our manufacturing processes we have in-house. And so we have designed this algorithm to take that into account. At the end, what's of interest is not to have a nice simulation, but to be able to manufacture this system using the technologies we have in our hands. So how does it work? We will do the design of the optical surfaces in-house. We are using DPI combined with freeform diamond turning to manufacture the molding tools. And then we put these molding tools into injection molding machine that we also have here in-house. And we have adapted and developed a special process to be able and to make sure the replication quality is sufficient for the application. Then we can dice the MLAs out of it, and we get the two final components. maybe one point that is of interest is into these components. Obviously, here we made it quite large for demonstration because we wanted to be able to measure centration and so on. But you can imagine these systems to be smaller than that. And the alignment between the two MLAs is a mechanical alignment, so there is no active alignment required here. Maybe bigger picture, what it looks like. So you can see it's 100% plastic part, no mask needed. And you have certain number of channels here, which are completely not fixed. So we can really adapt this to each request. This is what it looks like when we are combining the two elements. And basically, these systems can be used for ground projection, like this kind of arrow, for grayscale images, but also for, of course, headlights. These are 3 different type of applications we are currently working on. The status of this development, which we have been working on for a couple of years, is that we are now starting to get out with the presentations to tier 1 and OEM companies, and we are looking for partners to put this into demonstration for actual cars, if you are speaking about automotive. Some projects are already ongoing, but we are, of course, very interested to discuss that with anyone having interest to look further into it. And I think that's it for my presentation today.
Yes, perfect. Thank you so much, Jonas, for giving this presentation. And let me introduce the next speaker. Final speaker of the day, Sébastien from Alfamation. Sébastien, you can start your presentation. Thank you so much.
So yes, my name is Sébastien. I work for Alfamation, and I will be talking about functional testing of micro-optics and lighting units more generally for the automotive. All right. So the topic is of Alfamation is covering a lot of let's say different topics in the supply chain, and we are located in Italy, and we make automated test equipments. Most of our business is for automotive industry, and we test typically electronic units like central units, and we do have also competencies in optics. And we developed systems to test the optical features of displays, for example, for automotive. And we also developed a system to test micro-optics. And one of the application was for automotive. I'm going to talk about this just after in a few slides. Alfamation is now part of Intest Corporation, is an US-based company, publicly listed at the New York Stock Exchange, and is composed by 6 companies in 3 divisions, providing solutions, test solution, but also process solutions for semiconductors, for PCB testing, and electronics and so on. So what do we do at Alfamation? We have a very strong engineering capabilities covering a wide range of competencies from optics, software automation, mechanical engineering, electronics, firmware, software. So it allows us to provide a wide range of solutions. We developed in the past years, for example, instrumentation that we call Flex Media XM.
which are these small modules that you see here, and we also provide test systems, semi-automated or fully automated, depending on the application, where we can test PCBs or sub-components from products from systems. And we also have systems to test the final product at the end of the line, to test it electrically, functionally, optically, and to do some calibration also. So just a few words about the FlexMedia XM module. I put it here in this presentation because we are in the automotive industry. This topic is about automotive, and we use these modules to how do you say, to communicate with automotive components. When we test them, we sell these modules individually, and we develop them to be very flexible and modular. And it can be used, for example, lighting systems become more and more complex as a final product, and requires in some cases to have some communication with the car to enable some more complex lighting patterns and lighting features. And these modules can be used to communicate by using the standard protocols of automotive, and also to generate video signals or to analyze video signals that can be sent to a lighting system for the automotive. So we do integrate them on the test system that we produce, but we also provide them as a single unit to be used in laboratory, but also on third-party systems provider. So the main business of Alfamation, is to provide test systems, and one of them is we made it to test the MLAs. So we've seen this concept already a few times in today's webinar about decorative lighting or turn signal lighting made by MLAs. And we developed a test system which functionally tests these MLAs at wafer level. So you can see here, I think the animation is showing where you can see the inside of the tester, where you put the wafer on this chuck, and we do have a set of instruments and a light source, which allow us to illuminate the MLA and collect the light at the outputs of the MLA. So these MLAs are made to project light on a plane, typically tilted on the road, for example, for the welcome carpet application. And in the tester, what we do is we put a lens to focus the image on a sensor. So we acquire an image which is somehow small and with squished together, if I can say, because of the optical lens. And then we use an algorithm that we developed in-house in order to project the image as if it will be projected on the design projection plane. So in this case, it is as if you would see it on the street, and we transform it geometrically, but also in terms of intensity. You can see here that the end of the pattern on the image occurred on the camera is very bright, but then when you project it on the street, because it is far away from the MLA and also at shining on the street at a very shallow angle, it is actually having a very intensity which is much lower than the one you see on the camera. So this is allowing us to do a test at wafer level of the MLA, and we are looking at the intensity distribution, of course, the dimensions, and the sharpness of the image with this method. And this method is very powerful also, thanks to the fact that the camera sensor is mounted on a motorized stage. And this allows us also to acquire images which are designed to be projected on a curved plane. These MLAs, by the way they are working, can be set to project the image sharp, not only on a flat surface, but also on a curved surface. And in this case, what we do, I'm not sure this animation here on bottom is visible, but we scan with the sensor across the image, and we obtain, for example, these 3 images, which have different part of the pattern in focus in different position. We stitch them together to obtain a fully focused image, and then we, as we did before, we project it on the target plane, and we can analyze the image as if it would be projected on the target plane. The main advantage of this method, it's very compact, it's flexible, everything is motorized, so it can be just set up for different projection setup by managing a recipe on the tester itself. And it is very fast, very efficient, because all the light is coupled into the sensor. You have very low loss of light, and we can measure with a single acquisition, we can measure 1 MLA per second, so it's quite fast in terms of throughput. So to complete the how do you say, the overview of what Alfamation can do for lighting, we can also test sub-assemblies like control units for lighting, also PCB with the LEDs mounted on them. One of our companies in the Intest Corporation is called Aculogic. They have also flying probe system, which is also very good at testing PCBs with LEDs on top of them. We developed together with them modules to verify the LEDs, so verifying the color and the intensity of the LEDs on the PCB. And yeah, as I said before, we test displays. We can test different modules and components at different level of assembly up to the fully integrated product. So potentially with different kind of platforms, with different level of automation, different level of throughput, we can test, for example, the lighting modules fully integrated with the MLA, with the light source, with everything packaged together. This is also something that we can do by imagining, for example, a test station where we have both the optical test, but also electrical contacting in order to illuminate the device. And we could also test, for example, rear lamps or headlamps. Especially, I saw some concepts last year at DVN workshop of even more complex lighting with displays, LED displays, and so on. So all of these need video signals, this analysis to check that every pixels are working and so on, that they are uniform and so on. So all of these can be done automatically also with these kinds of test systems. And all of our systems are built to meet these requirements, especially when we talk about micro-optics. So we build all of them to meet high throughput requirements, to have very reliable testing thanks to calibration methods and the use of golden units to monitor the health of the tester over time. Everything also we try to optimize the cost, of course, because we come to a point where you want to go in production most of the time. So you need to tackle volume, but with a solution which is maybe not as sharp as the one that you have in the laboratory. So we are very good at making trade-offs to go to the point what you want to measure and what is critical for your production. And if necessary, also, this is the case for the wafer level testing, we make the testers to be clean room friendly. So that was it. It's a very brief summary. I invite you to contact me to ask questions. We will be showing at Productronica in Munich, mid of November. It is co-located with Semicon Europa, so maybe some of you will be going. You can meet my colleagues there, talk about our capabilities. There will be also sister company from Intes Corporation that will be together with us, so you can see the full competencies of the group if you can come see us. Thank you for your attention. If you have any questions.
Thank you so much, Sébastien. Thank you so much to our speakers here today. It was really nice to have you here. But as I said, a few words. So we are active in many markets and we are the entry point for anything related to micro-optics. So please take a look at our website, and from there you can also visit some of our other portals. So we also have this ecosystem for micro-optics where you can find, besides our partners, many other companies in the European value chain. So here you see an overview of other companies you can find in there. But of course, you can find our partners as our preferred suppliers. So that's in the organization registry. In the technical marketplace, you'll find a lot of different offerings in the field of micro-optics. And also there you can see any of the speakers. So you will see listings there of any of these speakers. And of course, you can see our partners as preferred suppliers, but also G-Square, Microrelleus, FORVIA HELLA, they are on there. And you can use the I'm interested in this listing to contact them directly. And then in the community, you can find any other relevant information. And then this is also maybe already a note to have your calendars marked for 25th June next year, where we will have the second edition of our summit, where we will bring together the value chain and potential customers. So we will do that during the Immersive Tech Week in parallel with the VR days, and the main topics will be consumer, automotive, general lighting, healthcare, optical communication, and security and branding. So here are some impressions of last year's summit. So we had about 40 presentations, we had an exhibition, and of course a lot of networking. So, but for more information, go to fabulous.eu, and then at the top of all of our websites, you can easily switch between the Fabulous website, the ecosystem, and the Summit website. So, thank you all so much for being here, to the attendees, to the speakers, and yeah, thank you for making it a fabulous webinar. And yeah, I'm looking forward to the next one. So, again, thank you all so much.
Thank you, Jessica.
Thank you.
Thank
Bye.
you. Goodbye.
Bye.